Either we can see the stars later on, see whether it counts as out later lah. But then, if not, then usual place will be just like going to the rooftop upstairs to like stargaze lah. So this week's talk, I'll be covering like what's known as the cosmic distance ladder, which is like what was originally written in the schedule. But you notice I sort of like changed the title a bit lah. So this is basically what it's about, which is like how do we know the distance to all the various stars and everything. So if you sort of been to my previous talks, one thing I always emphasize is that astronomers is like you can imagine the sky as like a celestial sphere, right? So it's a sphere with big stars at infinity, and then basically we can sort of know where is the direction of the star in the sky. So we can't really tell exactly like just how far is it away, like as measured away from Earth lah. So this is what this talk is about, which is how astronomers actually find that out. So actually this isn't as like strange as I guess we think it is, right? Which is like needing to use indirect techniques to measure distances. So for example, if you want to talk about measuring large distances on the surface of Earth, there are like disciplines of topography and geodesy, which really is all about all the various techniques as well as accuracy of the techniques we can use to like do like land surveying, to like map coastlines and everything. And all of this really relies on like all sorts of indirect techniques to establish like where exactly are you on the position of like on the surface of the Earth, right? And then from there they sort of like that calculate like whatever the distance between 2 points of Earth's surface is, right? So astronomy has sort of like a similar problem, just that it's even worse because it's confined into the solar system on the surface of the Earth, right? So we really can't like use like those kind of indirect techniques where you can move your position around. So just a historical background, the question of like just exactly how far the stars are away from us is a pretty important question, right? So it has sort of a cosmological significance. So cosmology generally just concerns itself with like things like what is the size, the shape, and the whole form of the entire universe, right? So back to the time of the ancient Greeks, right, like the Aristotelian cosmology, right? So they basically imagine the whole universe as a sphere, set of like crystalline concentric spheres, and then the outermost sphere is like the sphere containing the stars, like the firmament of the stars. So in effect, like in this Aristotelian worldview, right, the entire universe is exactly what being contained within this like sphere of like stars, right? So everything inside your planets, comets, whatever, and then your sun and Earth and Moon, that's basically all there is of the universe out there. So from there you can sort of see like the question of like just how far the stars are away from us directly tells us like the size of the universe and everything, right? So from there you can sort of like know like why the question of like the distance of the stars is such a contentious topic when it comes to like the Copernican revolution and everything, right? So during the Copernican revolution, there was a debate on whether like, the Earth and the celestial sphere revolves around the sun or the other way around, right? So one of the main principal effects that were like sort of brought out to challenge the Copernican view is that when you're standing right here on Earth and then you look outside at the stars, if you think that the Earth moves around the sun, you should be able to see a parallax effect, right? So the stars, they won't move around the Earth at constant speed, right? They'll be like shifting back and forth slightly, and then there'll be this like sort of like parallax effect happening. But the fact that you can't really see this at all, or at least using your naked eye or the best observing technique to catch that, sort of means that if the Earth is rotating around the sun, that means that this crystalline sphere containing the stars is so immensely big that it's like a size that's beyond like what people can imagine at that point in time. But as you know, eventually the Copernican view sort of like won out, and then this just led to like several new ideas about how the universe looks like, right? So starting from like the 1600s to 1700s, you have like authors such as like Bruno and Montanel. So they are more like science fiction writers. It basically helps like convey the idea that, you know, if you look out there, if all the stars you see out there like are so immensely distant from us, then we can maybe think of them as being like other stars as well, and each of them as being island universes containing their own like worlds, you know, so their own Earth, their own planets, their own moons and everything. And based on this, we also have the idea that different stars have different distances. So this stems from like the Copernican principle, right? So that our solar system does not occupy a unique place in like the universe. So if all the other stars are sized just like ours, then if you zoom out, you should expect them to be sort of like randomly distributed in space, right? So that's homogeneity. So that tells you that different stars, you expect them to have sort of like different distances from each other. And then from this different distance, then you have this kind of parallax effect going on, right? Where stars closer to us will like wobble with respect to more distant stars. So like the first accurate parallax measurement was done all the way in 1852 by Thomas Henderson using this kind of a weird instrument there. Don't ask me how it works, I have no idea. I've been staring at this for a long time and couldn't figure it out. Yeah, and then back then what he measured was the distance to Alpha Centauri, which some of you may know is like the closest star system away from us at about like 4 light years away. So during modern times, our understanding of like parallax and like the distance of stars has improved a lot, and most of them has really come from the existence of ground survey observatories and astrometric satellites, right? So before we had this kind of like automated observatories and like satellites, all that whatnot, we only had cataloged the parallaxes of only a very small amount of stars, maybe like a few thousand animals, right? No catalog. So our estimates on like the size and distances of stars is like hugely limited. Right? So, but with modern day observatories, these can give us like the range of distance measurements all the way up to like 500 parsecs, which is around 1600 light years, and just to give you some reference, the diameter of the Milky Way is around like 32,000 parsecs, right? And then the observable universe is around 28.5, okay, very big number, don't care. Easier way to understand this is probably to use a graphic. So, if we imagine like this is our whole galaxy, the earlier generation of astrometric satellite, the Cosmos, is just sort of a small dot over here. And then our newest, like better astrometric satellites can give us like this small circle right here. Right? So it's not even enough for us to like reach to like the nearest like spiral arm next to us. So because of this, that's why we need to build a system of like basically a ladder of distance measurement. Right? So we basically have a set of different measurement techniques, and different techniques are designed to basically cover different distance scales, right? So basically on the scale of like solar system to like nearer stars, further away star clusters, the galaxy, and other galaxies, and that's where we come like extra information. Right? So the first thing is that no single technique can cover all distance scales, so that's why we need all of them. And the second part of why it's called ladder is because the higher so-called rungs on the ladder are calibrated against the lower rungs on the ladder. So that means that if your techniques in the lower rungs are not well calibrated, maybe there are some inaccuracies here and there, all your errors in there will sort of propagate upwards, right? And that will make like all your measurements up there a lot less like accurate than it can be. So this is basically another look at the cosmic distance ladder, and this is roughly the structure that I'll be covering in my talk. So I've discussed like quite a bit about what the first round is, which is annual parallax, right? So this animation here basically gives you a very good like visualization of how parallax works in essence, right? So the stars that are moving the most are the foreground stars, while the stars all the way at the back, they look sort of like fixed in place just because they're like so far away, right? So and then from here, we intuitively can understand like volume and space from this because our eyes are designed to like sort of like understand what parallax is, right? So this really speaks to our intuitive understanding of distance. And not to mention, parallax is also like one of our most accurate distance measurements. Right? So this is basically a diagram of how parallax works. So in effect, as Earth orbits around the Sun, our angle with respect to a nearby star will change with respect to a distant star. And in effect, you can just treat like very, very distant stars just like fixed points. So, but in actual fact, if you go out, you take pictures of the stars and sort of like track their motion across the sky, you see that there are two components to the motion, right? So the first thing that you see that this weird like spiral thing happening. So this kind of like back and forth motion is exactly what this is parallax happening. And then there's another component of motion where the star is sort of like moving in this direction, like in this general direction, right? So that part of the motion is called the proper motion of the star, right? And there are several reasons for that. So the first thing is that the stars themselves are also like moving around the Milky Way. The second part of that is that the sun is also moving around the Milky Way, right? So they all have their own time motions. So basically, the proper motion of the star in this direction is, roughly speaking, the relative motion of the star with respect to the sun. And then all this very spirally like component comes from basically the orbit of Earth around the sun. So, in case you don't know, this distance right here is basically the radius of the orbit of Earth from the sun, and then we term this distance 1 astronomical unit. And from this, we can sort of like derive the parallax formula. You don't really have to know where this comes from and everything, right? So, but what I want to bring to you is that we can use the parallax method to sort of define an entirely new like unit of distance, right? So this unit of distance is what we call 1 parsec, which is defined as one astronomical unit divided by 1 arcsecond of parallax, right? So if we measure like basically we measure like one arcsecond of parallax, then we know the distance is 1 parsec. But what exactly is this 1 parsec? We don't really know, like, because the actual distance of this 1 parsec depends entirely on what is the length of this one astronomical unit. And if you're familiar with like Kepler's laws and all of that nonsense, then you might just say that, oh, you can just take the mass of the sun, and then we just plug that into like a formula, then we can sort of know. And then we also use like what is the length of a tropical year, like which is how long it takes for Earth to orbit on the sun. Then from that we can sort of like calculate what is the radius of Earth's orbit and Earth's 1 AU. But that's entirely backwards, because the whole reason we know what the mass of the sun is in the first place is because we know what 1 AU is. Then we use that as sort of like estimate like, and calculate the mass of the sun. So it's not, yeah, so 1 parsec is 3.26 light years. And just to give some perspective, the nearest star system again is around like 4 light years away, right, which is approximately. So that tells you that the biggest parallax you can observe in the sky is on the order of like around 1 arcsecond per year. So in order to sort of measure like the astronomical unit, yeah, historically there has been a lot of ways to do it. One of the most major milestones is using the Venus parallax to measure the astronomical unit. Right? So in fact, it was first proposed by Edmund Halley. This name I'm familiar to some of you. He's the same guy who discovered the Halley's comet. So the comet now bears his name. So the way he constructed his method is basically depending on where you are on the surface of the Earth. Right? So let's say you're on the celestial equator versus being somewhere all the way high up in latitude. Okay. From these two different locations, your angle relative to Venus and the Sun is sort of different, right? So because of this difference in latitude, the transit timing of Venus will sort of be different, right? So because if you're at a higher latitude, Venus will appear to cross the surface of the Sun at this lower region over here, which is like a shorter distance, right? As compared to someone on a more equatorial latitude, they will see Venus transiting the Sun at a higher point across the surface of the Sun. So that means this transit timing will be different depending on where you are on the surface of the Earth, right? And because on the surface of the Earth, our techniques of like topography and like map making has become so advanced enough that at that point we can know with quite good certainty like what is the distance between like two regions on Earth. Right? So from that is sort of like our baseline for taking all these measurements, right? So in effect, we can determine how far is Venus from us, and then from there, how far the Earth is away from the Sun, based on how far 2 points on the Earth's surface are separated by latitude. So this is how like, historically the astronomical unit was sort of like defined and discovered. So back then, the measurements were done at 4 times, one in 1761, 1769, 1874, and 1882. You might realize that something interesting about like Venus transits is that they always come in pairs one. So it's like you see one in 1661, you find one like around like, a few more years later to like some 69. So always occurs in this kind of weird like pair kind of pattern. Now in our modern era, we don't really use like the Venus parallax method anymore to sort of like determine the AU because it's sort of like limited accuracy. Right? So nowadays, what we do is that we sort of like use these gigantic radio telescopes. So what these radio telescopes do is more than just like collecting radio signals from the sky. Right? In fact, a lot of them have their own like power source where they can like send a radar beam all the way out into space. Then effectively they just bounce off like the radio pulse off the surface of the planet, right? So the concept is easy enough to remember. Radio waves are like a pair of electromagnetic waves, right? So that means they travel at the speed of light. And then if we send out a radio pulse signal towards like let's say a planet, then we just time the amount of time it takes for the reflector beam to go all the way towards the Earth. Then based on the speed of light, we sort of can like calculate just how far as the beam sort of travel like back and forth between the two like places, right? And from there we sort of like can calculate what exactly is the distance of a planet away from Earth. And in fact, this radar ranging technique is so good that we can basically just bounce like radio signals off like stuff like asteroids in the asteroid belt and sort of construct like a radar image of what the surface of the asteroid is, right? And in effect, what you're doing is that you're really just measuring distance over here, right? So the parts of the asteroid that are sort of near to us, they're like protruding in this shape. They'll basically like reach us faster than the further away parts, right? So basically from this, you can sort of tell just how accurate radar imaging is in like determining like astronomical distances away from us. And in summary, this is sort of like the uncertainty level of astronomical unit over the years. So our most modern like measurements are like ridiculously accurate. And precisely because our measurement of the astronomical unit is so precise, that means that the parallax method is also one of our most precise ways of determining the distances towards like the stars. Okay, again, I remind you that like parallax is still like quite limited in what you can do. So if you want to really map like even the structure of our own galaxy, you need to take one step further. So this is where like I start to introduce the idea of a standard candle. So if you have light coming from a roughly like spherical source, and when I say spherical, the object does not have to be spherical, right? If you have a candle, that's sort of a spherical source. Right? If you have a torchlight, it's sort of a spherical source, but then you're just cutting off the light around the boundaries, right? So in fact, a lot of things in the world follow this like inverse square law, right? The only things that don't are really like lasers, right? Where you use like some special lens to sort of like coordinate the focus of the beam so it doesn't fall off with like 1/r squared. So what this effectively tells you that if you know the original brightness of an object, and then you go measure how bright it appears to you, you can sort of like tell what the distance is, like how far the object is away from you. So standard candles are basically astrophysical objects with a known intrinsic brightness, right? So because you know the intrinsic brightness, based on the difference between its observed brightness and the intrinsic brightness, you can sort of like divide back the distance to the object. And in astronomy, we do this in terms of what's called the distance modulus. This sounds fancy, you have logarithm and everything, but this is really just because of the way astronomers define brightness in astronomical terms, which can get pretty annoying. But some examples of what standard candles are might be like star clusters, eccentric variables, like 1A supernovae, or like galaxies, right? So I'll be covering a bit of them in a while. So before I mentioned that the first round of the ladder is sort of like the parallax method, right? In order to do a bit more measurements, you have to climb to the next round, which is based on beam sequence fitting. So stars have like sort of like several properties that we can really observe in our telescope here, right? So the first property is how bright the stars appear to us, which is sort of like luminosity. Second is the spectra. So basically, we take the light coming from the star, we split into different wavelengths, and then we see how, like, what is the intensity of specific like wavelengths areas over. Yeah, basically, it's just a plot of the intensity against the wavelength. So basically, in atmosphere of stars, you have like certain like dips and like peaks, depending on like what the chemical composition of the star is and everything. But for our purposes, that isn't really an important thing, right? So the third thing is that stars have a color. And then we usually quantify this by what's known as color index. What this really is that you're just taking the brightness of the star in the blue wavelength and the brightness of the star in sort of like yellow wavelength and subtracting the two. And this is like more or less, like this number would be more or less a proxy for like whether a star is on the redder side of things or whether it's on the bluer side of things. Right? Yeah, so this will be the two we're focusing on. And effectively, if you plot the brightness of a star against its color, this will give you what's known as a color magnetic diagram, right? So you get this sort of like nice pattern over here. There's a mean band of like stars where like most of the stars in the universe are light on, which is what we call the mean sequence. And you do see like some other stars here and there that form like different patterns here and there, right? So this thing is also known as a Hertzsprung-Russell diagram, like HR diagram. Yeah, the pronunciation isn't that important. Yeah, so based on this, in fact, this thing is actually a standard candle by itself, right? The reason that this is a standard candle is that this sort of like mean sequence relation must follow your horizontal branch in giants. It applies for like absolute magnitude, which is how intrinsically bright an object So basically, you just take all the stars in the universe or any like random like selection of stars from here and there. You just throw it on this diagram. It should follow this pattern based on absolute magnitude. So if you have a random population of stars, you can use that as a standard candle because you know, like if you plot it on the diagram based on its color, it should follow this pattern. So this is the whole idea behind main sequence splitting. Like, so what we do in main sequence splitting is that we sort of like try to determine the distance of star clusters, right? So as you know, star clusters are groups of stars that are born from the same like molecular cloud, and because they are born from the same molecular cloud, they are sort of like gravitationally stuck together, they are bound together. And roughly speaking, that also means that they are at the same distance away, right? So that's really the most important part of the whole thing. So as you know, when we go out and measure like the brightness of stars in the sky, we don't actually measure its intrinsic brightness, right? We only measure how bright it is like from us. And that brightness can change a lot depending on like just how far away it is from us. But because all the stars in the star cluster are at the same distance away from us, even though we don't really know its intrinsic brightness, we still know that their relative brightness to each other must still be the same, right? They're only just like reduced by the same like proportional factor. So maybe they're reduced by 50%, 90%. It's all the same across like all stars in the star cluster. And that means that if we sort of like plot their color against how bright they appear to be, we should still get the same pattern, but the brightness is sort of like offset up and down by a certain amount. And this amount directly tells us just how far the star cluster is away from us. So the other thing that's important about this method that it works precisely because the color of a star is more or less not affected by the distance. But as you see, that assumption isn't exactly true. So in order to calibrate like this mean sequence method, we first need to use parallax as a sort of like a lower ladder to sort of calibrate it, right? So the way it's done is that there are certain star clusters that are very near us, right? So let's say the Pleiades cluster or the Hyades cluster. They are very nearby star clusters. And that means that they're close enough that we can use parallax in order to sort of like accurately determine what is the distance of like these individual stars to star cluster, right? And we know for sure based on the parallax method what their distance is away from us. Then from there we can sort of like plot their color magnitude diagram. And the color magnitude diagram being produced by this like reference star clusters is sort of like our reference star. This is our standard. We know for sure that the relationship between color and basically the brightness of an object must follow this relation. And basically you just compare other star clusters against this like standard reference number. So this is basically how the whole like mean sequence fitting method is calibrated. There are some limitations to this method though on like how far you can measure. So the first thing is that you need bright enough stars and star clusters to sort of like get the color index of a star. And similarly, fitting is only more accurate for like dimmer stars. Right? So if you look at the mean sequence here, you see like there are a lot of stars that occupy this region of the mean sequence, which is like the lower part. The lower part is where like all the stars are like sort of dimmer and they're on the radial side of things, right? As you know, dimmer stars, if they're further away, it becomes a lot more dimmer, right? So it becomes super hard to like measure accurately what the brightness is using like telescopes placed all the way on Earth. So as a result, we're sort of like limited in like how far we can use this method to determine how far these star classes are away from us. And the last thing, which is arguably like one of the most important points, is that in space, there's also stuff like gas and dust just floating about here and there. Well, sometimes we sort of like can estimate just how much of this gas and dust is. Sometimes we can't. And the thing is that all these like interstellar gas and dust, as light sort of like passes through them, gets scattered preferentially depending on like what its color is. So that means that blue wavelengths are scattered a lot more than red wavelengths. And that means that overall, if you look at a star from behind a dust cloud on every day or whatever, the light from the star tends to look redder than it actually is, right? And all of this sort of like leads to like systematic errors in like our distance measurements of these stars, right? And the effect is even worse if you go to further stars, right? Because if you think about it, logically speaking, if the stars are like further away from us, there's more space, and then there's like more potential for there to be random bits of like gas and dust to think about. So it becomes a result, the accuracy of this like mean sequence fitting method gets like limited at very large distances within our Milky Way, right? So we can estimate this range to be around like 10,000 parsecs or so. And if you put it on like the picture of the Milky Way, basically this is roughly how it looks like. So it's basically one quarter of the way around the galaxy. And it's still a very useful method because as you can see, this circle sort of encompasses like some of the nearby spiral arms here and there, right? So in fact, what astronomers have done is that they use this method to sort of like look at star clusters and they measure the distance of the star clusters and they use that to sort of like reconstruct what the structure of the Milky Way is, right? Because our Milky Way is structured such that all the gas and dust and all the nebulae are sort of like patterned in this list. And this is also where most of the star clusters being born are located, right? So this becomes a very, very good way for us to sort of like map out the local structure of our own Milky Way galaxy. And this is exactly a reason why we can like very confidently state like, oh yeah, we're in the Orion arm of the Milky Way galaxy. And there's like nearby arms of the Perseus arm, the Taurus arm, and whatnot, right? So it all comes from this like mean sequence fitting of star clusters. So in order to get to distances beyond this like small narrow stretch of our own Milky Way galaxy, we have to climb yet again another rung towards the next one, which is Cepheids variables, right? So this star here is known as Delta Cephei in Cepheus. So Cepheus is quite a northern constellation, right? It's all the way, it's very, very close to Polaris, right? So it's basically just like next to it. And this star, Delta Cephei, is sort of like the prototype star for this entire class of like variable stars or like Cepheids variables, right? So what are Cepheids variables? Basically, they are kind of stars that sort of like pulsate in brightness at a steady rate, right? So basically, periodically, they seem to like appear brighter, and then they are dimmer, they are tighter, and dimmer. So this graph sort of like exemplifies just how they look like that. So our axis over here is basically a plot of just how bright the Cepheids variable is, and the x-axis here is basically just time. So you can see its brightness sort of like fluctuates up and down, up and down, up and down, in this like nice, quite distinct sort of like zigzag or what you call jigsaw pattern like this. So some of them they don't look so sharp, but some of their peaks might look a bit offset here and there. But Cepheids variables generally follow this sort of like pattern, position pattern here and there. And you can see that its period is roughly on the order of days around here. So the thing about Cepheids variables that makes them sort of like useful as like distance measurement tools is that there is sort of a relationship between how bright a Cepheids variable is versus like how fast it is pulsating, right? So if your Cepheids variable is sort of brighter in color, no, not brighter in color, if it's brighter, then the period of this pulsation will be longer. So that means that you'll be like pulsating at a slower rate, but you'll be intrinsically brighter. So because the pulsation rate is something you sort of like can objectively measure, and it won't be affected by the distance away from us, we can use that to sort of like estimate just how intrinsically bright the Cepheids must be. And so that's how we can use Cepheids variables as sort of like a standard candle. And over here is the period luminosity relation. Again, not very important to know this, just like know the rough concept. So how are Cepheids variables like actually calibrated? So historically, Cepheids variables were sort of discovered by this astronomer called Astro. So what she did is that she basically was observing like stars in the small Magellanic Cloud. So in case you don't know what the small Magellanic Cloud is, it's like you can see the Milky Way in the foreground here, which is this like gigantic band across the sky. And in the southern sky, in like certain parts, you can see sort of like two dwarf galaxies over here. So they are galaxies, they are basically like a small galaxy that's sort of like distinct from the Milky Way, but it's sort of like orbiting in our own like gravitational influence. So this one's a large Magellanic Cloud, and this one's a small Magellanic Cloud. So she was basically observing stars in the small Magellanic Cloud, and she sort of like observed that there are certain kinds of stars in there that have this sort of like pulsation behavior with like a very similar like light curve pattern, right? So she basically took all of them and found the period luminosity relation. And the reason that you can even find the period luminosity relation is because, you know, when you look at the small Magellanic Cloud, it's a thing, right, out there in space. So logically speaking, all the stars in there must be roughly the same distance all the away from us in the Milky Way. So based on that, she basically just assumed like the apparent brightness of the Cepheids is sort of a good proxy for like the intrinsic brightness. Because their relative brightness relative to each other again is similar, yeah, this is exactly how we do like mean sequence fitting up, so it's a similar idea again. And from that, she established the period luminosity relation. But the thing is that it still isn't helpful for us to like use it as a distance measurement, because in the first place, we don't actually know how far the small measurement cloud is away from us, right? So at that point, there was a whole debate really about like just how big the universe is, right? And then people were looking at like all these party stuff in the sky, like nebulae and like galaxies and whatnot, and they were debating whether they were like outside of our own Milky Way galaxy or whether they were within it. So at that point, we don't really know like just how far the small measurement cloud is. But then the way that we do a calibration is that, in fact, the calibration was done by Edwin Hubble. He's like quite famous name. You all probably heard of him. He basically just found a Cepheid variable located within our own Milky Way galaxy, and it was close enough to be within the range of the mean sequence fitting method, right? So he basically found the Cepheid variable stuck in a star cluster, and from that he used mean sequence fitting to sort of figure out just how far away this star is away from us. And this star is what we now know as delta Cepheid. So that's why like delta Cepheid is our prototype star for calibrating the whole like Cepheid variable method of measuring distances. Right? And then I think there was a recent proposal on using another star RS-40, using some kind of like echo method. I have no idea what that means, but yeah. So for now, delta Cepheid is still like our source of calibration for this like period luminosity relationship. So Cepheids are like quite prominent historically just because they play a huge role in the Shapley-Curtis debate, right? So yeah, that was when like they were debating on the nature of like the Milky Way galaxy and whether it's like the whole universe. And like at that point, the things that we call galaxies were also called spiral nebulae. So they were debating on whether like this spiral nebulae were outside our own galaxy. And the distance to the Andromeda galaxy was like measured using Cepheid variables, right? So at that point, Edwin Hubble, he used the period luminosity relation established by Henry Leavitt to sort of like figure out just how far away the Andromeda galaxy is away from us. And you can sort of see this in like Edwin Hubble's original photographic plate. Right, so photographic plate is basically like your old like camera film, but they use it for astronomical purposes. So he was basically like circling here, and he was basically just looking at it and identifying where all the Cepheids are. Basically. So it's a very, very traditional method, nothing like the high-tech like astronomy that we expect. So imagine you're just taking photographic plates and I just like taking them in my hand. So it was like a really interesting photo. Yeah. But then back then the distance he measured was about like 900,000 light years. In comparison to the size of the Milky Way, which is on the order of 3,000 light years. So at that point, we already sort of knew what the size of the Milky Way is, right? Because we were measuring distances to star clusters and whatnot, and then from there we can sort of estimate what the size of the Milky Way is. So Edwin Hubble's measurements made it very, very clear that the Andromeda galaxy lies very, very far away from our own like Milky Way galaxy. And then from then on, we also like went on to measure like the Cepheids in other galaxies here and there to sort of like establish that distance. Yeah. So in fact, our modern measurements to Andromeda are quite very, very different from what we measured back then. Right? So back then, we were measuring 900,000 light years. Our modern day estimate is that like Andromeda is 2.5 million light years away. So that's an error that's like more than double of what you originally measured, which is like quite a huge error bar, right? If you think about it. And does that mean like the whole Cepheid variable method isn't really accurate? So what actually happened is that it turns out that the Cepheid variables we saw in Andromeda was sort of a different kind of Cepheid variables. It was like calibrating them against in the Milky Way galaxy. So these are what we call like type 1 versus type 2 Cepheid variables, right? So so this discrepancy was something that was only discovered later on, and it revised a lot of distance measurements to the universe, right? So this sort of like shows you like one of the pitfalls of using all these things as distance measurements, right? Because we're sort of like assuming, oh yeah, there's this one type of object here in this part of the galaxy and another part of the universe. And we're assuming that all of them are really like the same thing, right? But maybe it might turn out that they're not really behaving the same way. And this is something that has like historically happened with Cepheid variables. Yeah. So here are just like some of the limitations. The nice thing about Cepheid variables is that, yes?
What's the difference between type 1 and type 2?
The main difference is whether they are population 1 or population 2 star. So the difference between a population 1 and population 2 star depends on the metallicity of the star, which is just how much like heavy metals are there within like the star itself, right? So basically this has like, I don't know, it just has consequences for like how like the thermodynamics of the star works, right? So it sort of changes the period luminosity relation. Yeah. So the thing about Cepheid variables is that they are very, very luminous, right? So you can see that if you plot them in the H1 diagram, they are the stars that lie on this area. So they are on like the brighter side of like all stars that are possible in the universe, right? So you can imagine them to be all those big like supergiants or whatever. So because they are so large and so bright, they are even visible in other nearby galaxies, right? So that means that we can use Cepheid variables to measure distances to like our nearby local group. And historically, we even use it to sort of like discover the distance of galaxies in the Virgo cluster, right? So in case you don't know what the Virgo cluster is, it's like literally you look in the direction of the Virgo constellation Virgo. It's like you just see a whole bunch of galaxies like there, just right there, right? And it's a very popular like astrophotography target, right? Because it can image like basically a whole galaxy cluster over there in a single like frame, right? And then, like one of the most famous targets in like Macaulay over there. Yeah. So it's basically a nearby cluster of galaxies, not in our local group, but it's like basically beside it. And we use like the Cepheid method to sort of like establish just how far away it is from our own Milky Way galaxy. Right. So some of the limitations, I did mention before that there was a whole like shit show with like type 1 and type 2 Cepheid variables. But even until today, astronomers are still not very, very sure about just how like the composition and the metallicity of stars will affect this like period-luminosity relation. Right? So this is like one of the biggest like issues the cosmic distance ladder is. So this is like one of the possible sources of error in our modern day like distance measurements in nearby galaxies. Right? Yeah. So just to get a sense of just how far this distance is away from us, this is the local galactic group, right? So the local galactic group basically is made out of like two members, the Milky Way and the Andromeda galaxy. And a lot of the other galaxies in the local group are basically those kind of like small elliptical galaxies, but they are trapped within the gravity well of like the Milky Way and Andromeda galaxy. So you can see the Milky Way right here. You can see the large and small magnetic clouds. It's a bit small in the diagram. And then you have the Andromeda galaxy. So all the distances within this local galactic group have been like very firmly established using like Cepheid variable methods, right? And if you zoom out a bit, this is our local supercluster. Right? So over here, you probably can't see the words clearly, but this is the Virgo cluster. And the local group is all the way here. So it's like a very sparse region of space. And there isn't really much galaxies nearby us that are really affecting us or anything. So in effect, the Cepheid variable method is accurate enough that it can basically cover most of like the galaxies in this like Lania Kea like supercluster. So all the way until Virgo cluster, then we can sort of estimate this is just how far we can measure using Cepheid variables. This seems like quite a lot, right? But even this like supercluster is only like a very small, tiny part of like observable universe. So okay, this is not observable universe, but then this is basically a map like all the local superclusters and stuff like that. So basically our Cepheid method can only pick up in this like, small region of space, right? So based on this, even though Cepheid can like measure the distance of other galaxies, still need sort of like other methods to climb again like one more rung on the distance ladder in order to get us to like the stage where we can measure like the distances of all these like superclusters here and there, right? And then this is important because when we discuss cosmology or about the large scale structure of galaxies, we need to be sure about our distance measurements to all those galaxy clusters, right? And from there we can sort of construct a map of like what is the structure and just how dense the universe is. And this has like implications on like our theories of like cosmological extension and whatnot. So the fourth galactic rung, the fourth rung on the cosmic ladder is not a single rung, right? I call it extragalactic indicators because it really looks more like a whole web of like distance indicators, right? And I'm telling you, I don't really understand all of them either, right? So I don't like forcefully do it like inflict mental torture of all of it. But then the main point of me showing this graphic is to like really illustrate that when it gets to this stage, there isn't really one way to measure things, right? So what astronomers do is that they just keep trying to think of new ways to do distance measurements. They propose it, try to check it against other distance measurements, and then see if it works or if it fails, or if there's a disagreement, we also can't be sure which is the wrong one, which is the right one. Yeah, so it's a very messy process of like figuring out like what's the best distance measurement, what may not work so well. But the most like important extragalactic indicators are the ones that are right here. So type 1a supernovae with Halley-Fisher relation, and then we have what are called luminous function vectors, right? So all of the ones that are listed here, they are actually standard Cantor measurements, right? So basically, all of this just describes a kind of object that one way or another can sort of like tell just how intrinsically bright it is. And then from there, you can sort of like define just how far it is away from us. Right, so for type 1a supernovae, this is probably one of the more familiar ones because historically it has been sort of used to really establish like just how fast like the universe is expanding and all that, right? So type 1a supernovae is basically like when you have a mass transfer in a white dwarf binary pair, right? So you have a white dwarf which is sort of like a leftover remnant of a low mass star like our sun, right? So as the star like our sun reaches the end of its lifespan, its outer atmosphere will sort of like inflate and then drift off to space because the gravity isn't like strong enough to hold it back anymore. And then what's left is sort of this core, then called known as the white dwarf, right? So this like type of supernovae sort of happens in binary star pairs, right? Where one of the stars has sort of like died already and then has become a white dwarf, but it's still close enough that it starts like basically sucking material from like the other companion star, and basically keeps accreting like so much like stuff from its partner star that eventually it gets too heavy to support itself and then it explodes in supernovae. So the thing about supernovae that it has like what's called a characteristic light curve, right? So basically the brightness will like suddenly shoot up very quickly and then you'll basically follow almost like exponential decay curve over time, right? So the thing is that it's sort of like predicted using theoretical like astrophysical models of like this like supernovae. And then we sort of expect this peak brightness to be like more or less consistent every time there is a supernovae. Right? So this is literally a standard Cantor in the most direct sense of the word, right? Supernovae have more or less the same brightness no matter like where it is in the universe. So and then not to mention supernovae are also like very, very bright and luminous objects, right? So basically you can see them from a very, very, very far distance away. So that makes them like a very useful object for basically measuring distance to like very far away galaxies and whatnot. Of course, like type 1a supernovae has its difficulties, right? So basically this is like a very transient phenomenon. It happens over a period of like a number of days, like tens of days. Like, so that means that if you don't like keep observing the sky and like keep tracking the sky for supernovae, you won't be able to catch them. You miss it and then you miss a chance to use it to do like distance measurements and all that. So that's why we like send like satellites and observations all the way up in space with basically like wide field cameras, right? So they're basically staring at large parts of the sky, basically just tracking the positions of stars and whatnot. And then anytime there is something like a new star popping up, you'll basically like relay this message to like this kind of like astronomical like news network. I forgot what's the exact name for it. So basically they have a whole network for alerting astronomers whenever a new supernova comes up. So yeah, this is like part of the reason why those supernovas are very hard to catch. The second method which is like slightly more reliable is like known as tardy-Fisher relation. And the idea is actually not too difficult to grasp. So basically bigger galaxies spin faster, more or less. Right? And the thing is that bigger spiral galaxies, they are always brighter, which makes sense, right? Because if a galaxy is bigger, it's heavier, that means it contains more mass, right? It contains more stars in it. And if it has more stars in it, it must be an intrinsically brighter galaxy, right? And the fact that it spins faster is sort of like something we sort of intuitively know from like, Newtonian gravity, right? So we know that the center of the mass of the galaxy is larger, so that means that all the stars orbiting around it at a set distance must be orbiting it at sort of like a faster rate, right? So that tells us that there is very roughly a relationship between how fast the galaxy is rotating versus like how intrinsically bright it is. And from that, because we know how intrinsically bright it is, we can sort of like tell just how far away this galaxy is away from us, right? So there is actually a similar relationship for elliptical galaxies called the Jacobi-Jackson relation. It's just that this relation is sort of like slightly different. Yeah. So I think this is like quite easy to understand, how at least I thought it was. Oh yeah, but then if you're wondering just how on Earth do they actually measure this rotational speed of the galaxy, it's through a method called like Doppler shift bar. So basically, if you like measure a galaxy and then you split the light from it into a spectrum, you know that galaxies sort of like have a pattern in their spectra. Then you can sort of see like actually there's an opportunity for me to explain this better in detail. So I'll just leave it for now. So So the next two methods are known as like luminosity function methods, right? So what this tells us is that populations of stuff like globular clusters of branching nebulae, they have a fixed distribution by absolute magnitude, right? So basically, if you look at all the branching nebulae within the same galaxy, right? So they're all roughly the same distance away from us. And then you basically just plot them, you just plot how many of them are there in a galaxy based on how wide they are, right? You know that they will follow a particular distribution, right? So basically, a galaxy will always have like this amount of like branching nebulae at this brightness, and some of them at this brightness, some of them at this brightness, some of them at this brightness. And then at some point, there will be a color point, right? So there will be no branching nebulae that are dimmer at this point in a galaxy. So basically, it's a similar idea to the whole mean sequence fitting thing, right? So basically, we take a whole population of objects. We know that their distribution must follow this particular pattern. So this thing basically acts as our like sort of like standard candle for like determining distance to like a galaxy. And the same idea can be done for like globular clusters, right? So basically, if you plot out all the globular clusters within a single galaxy in around the same distance away from us, it sort of like follows this sort of like curved shape with a peak over here, right? So based on this, based on like where the peak is as we like plot out for different galaxies, we can sort of tell like just how far away like this galaxy is away from us, right? So it's all again the similar idea of like mean sequence fitting here. So with all the extragalactic indicators, we sort of use it to really establish like just how far away all of distant galaxies are away from us. And all of that will sort of like bring us towards like the final rung of this like cosmic distance ladder, which is known as like Hubble's law. Right? So the first thing you need to know is that light sort of like experiences this phenomenon called Doppler shift. Right? So if I have an object emitting light or sound wave or in fact any kind of like radiation or whatever, if it moves towards you would see it like becoming like lower than usual, right? So all the signals from it are like higher in frequency. Then you see it like moving away from you, all the light coming from the object would sort of be like greater than you expect it to be, right? So you basically can use like this change in color as like sort of a proxy for how fast something is like moving towards us or how fast is it like moving away from us. So how do we actually know like how do we actually tell like what is this like magnitude in change, right? So the thing is that if we look at galaxies and then we sort of like check its wavelength versus like intensity, we can get this galactic spectra. And then the thing is that the spectra of a galaxy sort of has a very distinct pattern, right? So for stuff like spiral galaxies, you sort of see these like very sharp peaks here and there, right? So this is known as the H alpha line. And this is really because that in spiral galaxies, you sort of like have nebulae, right? And you have all the stars being like born in the nebulae, and this lasting radiation, and then you have all the emission nebulae here, right? So basically, the emission nebulae is like emitting very strongly in this H alpha line, and then that means that you have this like very sharp emission over here. So basically, based on like this position of the peak, whether it's shifted here or shifted there, you can sort of use that to calculate like just how fast the galaxy is moving over here towards us. And you actually have a similar idea for elliptical galaxies, but instead of this sharp peak, what you have is sort of like this like a dip in the intensity, which is known as the absorption line. And this is because that all of this sort of like reflects the absorption lines that are contained within the atmosphere of a star. So for elliptical galaxies, unlike spiral galaxies, you don't really have emission nebulae in there, right? Because all the gas and dust is like not really right there. So that means that its spectra is sort of dominated by the spectra of like stars itself. So you can apply a similar idea. You can check all the absorption lines, and then you can sort of check just how far back and forth has it been shifted by its like own motion, right? So from all of that, you sort of like calculate the velocity of the galaxy, and just how fast is it moving away or towards us. So historically speaking, redshift measurements have like been established like for a very long time, right? So back then, this astronomer called Astro, he sort of measured the redshift of galaxies. He sort of like established that, hey, there's something weird about these galaxies, right? Because many of the galaxies in the sky somehow seem to be like moving very quickly away from us for some reason. Then in 1929, Hubble again he used like satellites to sort of like establish the distance to roughly around like 24 galaxies within like the local group and like the nearby galaxy clusters, right? So he basically plot this out all in this graph. This is like an original graph that was like reproduced from his paper he basically just like plot it out, and then he says that, oh yeah, there is this linear relationship between like how far a galaxy is away from Mars versus how fast it is moving away from Mars, right? So he's saying that nearby galaxies, they are moving slowly away from Mars, but for very far away galaxies, they're moving very quickly away from Mars. And so this exact relation is captured in what's known as Hubble's law. So V on this slide is known as like the recessional velocity of the galaxy. So basically, how fast is it moving away from Mars? D over here is sort of like its distance away from Mars, and usually like that's in meter parsecs, and then H naught is known as the Hubble's constant, which is exactly the slope of this like line over here. And if you look at this graph over here, there's actually a very big variation, right? So it's not like all the galaxies are very nicely like lying down on this like straight line here. They're actually like scattered here, there, like quite a bit, right? So the reason for that is basically like galaxies, they're also like interacting with each other, right? They're also affected by their own gravity, so they're also moving about by itself. So actually, if you think about it, it's actually very difficult to establish this like Hubble's law. You really need a lot of data, a lot of like, galaxies to sort of like be sure that you're measuring the correct thing. So in fact, we have done that in modern times, right? So in modern times, we have like sort of like measured the redshift of so many galaxies and sort of like mapped them out. And this is basically a very, very nice visual representation of Hubble's law. So the galaxies around here are all like further away from us in objective terms. And then the color here represents like this redshift, right? So the redder it is, the faster it is moving away from us. So from here you can sort of see a graphical representation of like how everything is moving away from us. And over here is what's known as the zone of avoidance. All it means is that this is like a part of the Milky Way, where the Milky Way's core is, right? So it's basically just blocking out sight to all the galaxies behind it. So we can't really measure anything over there. So all of this has sort of like resulted in what's known as Hubble tension in cosmology. So this really occurs because there's two ways of like measuring Hubble's constant, right? So the first method is the familiar one we really talk about, right? So we use like parallax to sort of like establish mean sequence fitting all the way to separate variables and all electromagnetic indicators, right? And then we use it to like establish the use of like supernovae as sort of like the distance indicator. And we use it to sort of like establish the Hubble's constant again. The second one is a bit more different, right? So that one is based on a theoretical model of the universe, which is known as the lambda vector model. So basically, there is like a theoretical model, and there's sort of like parameters for like how dense the universe is and all of that, right? So from all that, we basically look at what's known as cosmic microwave background, to fill in the parameters of this model. And out comes the model, like a prediction for what Hubble's constant is, right? And basically, these two methods sort of like disagree very definitely on what Hubble's constant should be, right? So from this graph, you can sort of see all the blue measurements here are measurements using the cosmic distance ladder. And it gives us like a Hubble's constant on like around like 73.0 kilometers per meter parsec. And then for the lambda CDM method, it sort of like gave us measurements like towards this lower end of the range, like less than 70, right? In case you don't know what all the letters here are, you'll see some familiar letters here. HST is the Hubble Space Telescope. Gaia is the astrometric satellite I was talking about. And then, yeah, some of the other ones are a bit unfamiliar. They are like older projects. Over here, we have the Planck satellite, and then the Y satellite, right? So they are basically satellites for measuring the microwave range of the sky. So they are basically just sent out there specifically to measure the cosmic microwave background. And from here, you can sort of see there's a very big discrepancy.
What's that green line?
Oh, green line, those are using, they are using like gravitational waves. Right, so people are also trying to like establish new methods to sort of like measure and sort of Hubble tension. But at that point, the accuracy wasn't too good. And then, I don't know, there was this recent paper they were claiming that they have a measurement in the middle of the road, which is a bit confusing because like gravitational wave methods are sort of like not established yet. So there's still quite a bit of uncertainty on whether this is a good measurement or not, or whether there's like something else going on here. But yeah, for more better explanation of like what this whole like Hubble tension thing is and what it means for like cosmology, do you can please see? Wait, does any wait? Huh? I think you enable that.
The search for a single number, the Hubble constant, the rate of expansion of our universe.
Is it too loud? Gabby, what's the volume control?
The search for a single number, the Hubble constant, the rate. The search for a single number, the Hubble constant, the rate of expansion of our universe, has consumed astronomers for generations. Finally, two powerful and independent methods have refined its measurement to unprecedented precision. The only problem is that they don't agree. And this calls into question some of our most basic assumptions about the universe. In 1929, Edwin Hubble discovered the universe. He gave us our first incontrovertible proof that there are galaxies outside the Milky Way. The search for a single number, the Hubble constant, the rate of expansion of our universe, has consumed astronomers for generations. Finally, two powerful and independent methods have refined its measurement to unprecedented precision. The only problem is that they don't agree. And this calls into question some of our most basic assumptions about the universe. The search for a single number, the Hubble constant, the rate of expansion of our universe, has consumed us. In 1929, Edwin Hubble discovered the universe. He gave us our first incontrovertible proof that there are galaxies outside the Milky Way by measuring the distances to the spiral nebulae. They were many millions of light years from us, far outside the Milky Way, and so must be galaxies in their own right. Combined with the Doppler shift velocity measurements of Vesto Slipher, Hubble revealed that the galaxies are not only receding from us, but they are receding at a rate proportional to their distance. An impossibly vast universe had been discovered beyond the Milky Way, and at the same time that universe was revealed to be expanding. The galaxies appear to be racing away from us because the intervening space is expanding. We encapsulate the expansion of the universe with a single number called the Hubble constant, h0. It tells us how fast the galaxies appear to be retreating from us, dependent on their distance apart. But more fundamentally, h0 tells us the rate of expansion of the universe. The search for a single number, the Hubble constant, the rate of expansion of our universe, has consumed astronomers for generations. Finally, two powerful and independent methods have refined its measurement to unprecedented precision. The only problem is that they don't agree. And this calls into question some of the best we could do was to estimate h0 to within a factor of 2, somewhere between 50 and 100 kilometers per second per megaparsec. These strange units warrant some explanation. Kilometers per second, that's for the recession speed of a given galaxy. Megaparsecs is for its distance, with 1 megaparsec being around 3.3 million light years. If the Hubble constant were, say, 75 kilometers per second per megaparsec, then for every 1 megaparsec distance, we expect the galaxy to be retreating from us at an additional 75 kilometers per second. Historically, measurement of the Hubble constant meant measuring the recession velocity and distance for as many galaxies as possible. The velocity part is relatively easy. Just do what Vesto Slipher did and measure redshift. This is the lengthening of the wavelengths of light from that galaxy, which was stretched as it travels to us through an expanding universe. But distance, that's tricky. Hubble used Cepheid variables. Giant stars that are in the last phases of their lives. They pulsate with a period that's related to their true brightness, as discovered by Henrietta Leavitt. Measuring Cepheid periods in other galaxies gave Hubble their true brightnesses as though undimmed by distance. Cepheids became what we call standard candles, objects of known luminosity, whose observed brightness therefore tells us their distance. But this calculation involves assumptions and uncertainties. For one thing, the Cepheid period luminosity relationship first had to be calibrated based on nearby Cepheids whose distances can be figured using stellar parallax, tracking their tiny motions on the sky as Earth orbits the Sun. This stepwise determination of astronomical distances is called the cosmic distance ladder. With each step on the ladder, uncertainties compound. Add this to our uncertainties in the behaviour and observation of Cepheids themselves, and the precise measurement of the Hubble constant has been a slow, laborious process. As larger telescopes and more expansive surveys were completed, we gradually whittled down the errors in H0. An important advance was the development of new standard candles. Cepheids are good, but can only be seen out to a certain distance. Supernovae can be seen much further, and type 1a supernovae are the key. These result when white dwarfs, ancient remnants of dead stars, absorb too much material from a binary partner. Runaway fusion causes them to detonate. The resulting explosion has highly predictable brightness, making them excellent standard candles. In the 1990s, astronomers were using these supernovae to better nail down the Hubble constant. They inadvertently discovered that the expansion of the universe is actually accelerating, revealing the existence of dark energy. One of the Nobel Prize-winning researchers behind this discovery is Adam Riess. Riess has continued the quest to refine our measurement of H0 to ever greater precision. A big part of his work is to improve the calibration of type 1a supernovae as standard candles. Riess's Supernova H0 for the Equation of State project, SHOES, uses the Hubble Space Telescope to match all supernova observations with new, more reliable Cepheid variables. By improving this rung on the cosmic distance ladder, all past supernova distances also improve. Riess and team have now narrowed down the Hubble constant to 73.5 plus or minus 1.7 kilometers per second per megaparsec. That 2%-ish uncertainty is a hell of a lot better than the old factor of 2 uncertainty. So where's the crisis? Well, in order to fully believe a measurement like this, we prefer it to be made through independent methods. The SHOES project measures the recession of galaxies up to around 2 billion light years away, so it's a more or less direct measurement of the current expansion rate. But there's another way to go. What if we could measure the expansion rate of the universe at the very beginning? Then we could figure out what its current expansion rate should be, given our best understanding of all the gravitational influences that affected that expansion since the Big Bang. So we'd better hope that it does give the same result, or there is a big problem with either our supernova measurements or with our understanding of how the universe evolved. Spoiler, there is a problem. There's another reason to try to calculate H0 from observation of the early universe. It's that observation I'm referring to is far more reliable than Cepheids and supernovae. I'm talking about the cosmic microwave background radiation, the CMB. This is a topic we've been over, so for now just the TLDR. The cosmic microwave background is the remnant heat glow of the universe's initial hot, dense state, released around 400,000 years after the Big Bang, when the universe had finally cooled down enough to become transparent to light. We still see it today, now stretched by a factor of 1100 by its near 14 billion year journey through an expanding universe. This is the map of the CMB across the entire sky, created by the Planck satellite. The speckles are tiny differences in temperature corresponding to tiny differences in density. The blue regions are a factor of 1 in 100,000 cooler than the red regions, and also slightly more dense. These overdensities would go on to collapse into the vast clusters of galaxies of the modern universe. So, how can the CMB tell us the Hubble constant? The key is the sizes of those speckles. In the era just before the release of the CMB, matter and light were trapped together. Matter wanted to collapse under its own gravity, while light generated a powerful pressure to resist that collapse. These counteractive forces produced oscillations, really vast sound waves that rippled across the universe. These are the baryon acoustic oscillations, and they occurred on all different size scales, sloshing between high and low density over those 400,000 years. Then, the release of the CMB meant that light and matter were no longer coupled together, and so those oscillations stopped. The state of the oscillations at the moment of that release is imprinted on the CMB in those speckles. We usually show the distribution of speckle sizes with what we call a power spectrum. which basically shows the abundance of speckles of different sizes. The location of these peaks tells us which oscillation modes just happen to be at their peaks at the moment the CMB was released. This in turn depends on the density of matter and radiation, as well as the expansion rate of the universe in that early epoch. So how do you get the Hubble constant, the current expansion rate, from all of this? Well, first you figure out what starting cosmological parameters could give the power spectrum observed by Planck. Those parameters include the starting combination of both dark and light matter and radiation, as well as the initial expansion rate. And then you figure out how the universe described by these parameters should evolve to the present day. This sounds involved, but the Planck power spectrum is so rich with information that the Planck team claim to have calculated H0 to even better precision than Schu's. The problem is the results don't agree. The Planck H0 is 66.9 plus or minus 0.6 kilometers per second per megaparsec, compared to the supernova result of 73.5 plus or minus 1.7. Now, they're actually remarkably close, given we figured them out from data at the opposite ends of time, but they also seem irreconcilably different. 3.7 sigma different, in fact, which means a 1 in 7,000 chance that that level of difference could have happened through random errors. This is the crisis in cosmology. This discrepancy first emerged in 2016 when RIS's new calibration of the supernova-derived H0 revealed it to be in real conflict with the Planck result from a couple of years earlier. Since then, calibrations have been improved, results have been rechecked, and independent methods have been used to calibrate the supernova as standard candles. The difference is real, and in fact the error bars are only getting smaller. Okay, before we declare all cosmology broken, let's think about the two main possible sources of this discrepancy. First, there are unknown systematic sources of uncertainty in either the supernova or Planck measurements, biases that are driving one or the other to be too high or too low. Perhaps we don't understand Cepheid variables like we thought, or perhaps gravitational lensing alters the Planck speckles differently to how we thought. Ongoing efforts are ruling out systematic errors one by one, but it's possible there's still something we haven't thought of yet. Second, there's some unknown physics that needs to be taken into account for the CMB calculation. This is the most exciting possibility. There are a few options, so let's start a new list. 1. A new type of very fast-moving particle in sufficient numbers could skew the energy balance of the early universe and mess up the calculation. That particle could be the sterile neutrino, a hypothetical non-interacting neutrino that isn't part of the standard model. 2. Dark matter particles behave differently to how we thought. Perhaps dark matter interacts more strongly with matter and radiation, which would shift the sizes of those CMB speckles. 3. Dark energy isn't constant. The current calculations assume that dark energy is described by the cosmological constant, which by definition doesn't change. But if dark energy increases, that could explain why we observe a higher H0 in the modern universe than is predicted by extrapolating from the early universe. The answer will depend on whether the more correct measurement of the Hubble constant comes from Planck or Schu's. New observations and new telescopes will refine these numbers even further. Independent methods, like using gravitational lensing or gravitational waves, will weigh in on one side or the other. Perhaps the uncertainties will be refined and the two results will converge. That'd be cool. The near-century-long quest to measure the expansion rate of the universe will be concluded. Or perhaps the discrepancy will persist. That will be even cooler. We'll have a new tool to investigate the mysterious physics of dark energy, dark matter, or of unknown particles beyond the standard model. For now, we continue our obsessive quest for H0 and for what it'll tell us of the origin and fate of our expanding space-time. In today's comment responses, we need to catch up on 2 episodes. First, it's our Journal Club on Dr. Jamie Farn's paper about negative mass dark fluid as a unifying explanation of both dark